SIR has provided technical support and expertise to projects in Australia, Finland, Vietnam, Russia, Turkey, etc. SIR is responsible for proposal activities, preparing estimates, designing and developing technology, and on-site implementation in projects related to structural health monitoring, advanced composites, rehabilitation, and remedial engineering. Previously, SIR has worked as an independent structural and SHM consultant, SCMCES Bangalore. During this period, additional to consultancy projects, SIR has worked as a visiting faculty for various engineering institutes as well and has conducted free educational training programs on various subjects in structural engineering and structural health monitoring. Apart from this, SIR has other working experiences like design and site engineering, structural engineer, technical manager, MRRM, development scientist and manager SHM with SAVCOR, etc. In his private capacity, SIR has published and presented more than 25 papers in international and national conferences, also has social responsibility to contribute education system, has trained more than 40 interns, guided 20 plus postgraduate MTech ME theses on topics related to SHM, structural dynamics, earthquake engineering, FEA, remedial engineering, and structural engineering. His current research interests include SHM, structural dynamics, and earthquake engineering, seismic retrofits, advanced composite for structural retrofits, rehabilitation, and remedial engineering. SIR has been nominated as a peer review committee and the review board for international conference in India. SIR has been honored as Best Professor in Civil Engineering Studies at 27th Devang Mehta Business School Award 2019. Presently, SIR is an active member of ACCE, ISSS, ISWE, ISET, ISTE, IRC, IIBE, IGS, ICI, ARP, and QCFOI. A cordial welcome to you, sir.
Sir, over to you, sir. Sir, it is visible, sir, but your voice is little bit low, sir.
Is it still low now? Is it fine now?
Yes, sir. Sir, your sound is good, but the background noise is there, sir.
Okay.
Little bit noise is there, sir. Yes.
Okay. I will try to reduce it. Is it fine now or still you have the noise? Just give me a second. I
Yeah.
think things are
Yes,
going.
sir.
Is it
Yes, sir.
fine
We
now?
will wait, sir. Now it's okay, sir. Yes, sir.
Let me know because I'll be continuously making a presentation.
Yeah, sir.
Is it
But
fine
noise
now?
is there, sir. Sir,
This
noise
noise is
is
there.
there, sir.
Kindly excuse me for
Yeah.
a minute. I will try to fix the camera.
Yeah, sure, sir. Yes, sir. We will wait, sir.
I'll be kindly excuse me.
So participants kindly wait. The resource person is checking with the audio. So please hold on.
Prabhu, sir, voice is not there. Is
Ma'am, yes, ma'am. There is a background noise, ma'am. Sir is checking with that, ma'am. Okay.
Dr. Prabhu? Dr. Prabhu? Am I audible to all?
Yeah, yes, sir. You're audible, sir. Now the voice is good, sir. No problem, sir.
Thank you.
Yes,
Thank
sir.
you.
Thank you, sir. Thank you, sir.
Yep, please. Thank you. So thank you for joining for this online FTP. I'm extremely sorry for the initial hiccup we had, and there's always, a good beginning always begins with some type of such type of obstacles. So greetings to all present. I thank the organizers and the organizing institute Sona College of Technology for inviting me as a speaker for this 1 week faculty development program on the digital transformation trends in construction industry. So on behalf of my department and PS University, I wish the organizers and the hosting institute and the department a grand success. And I must be very thankful to Dr. Prabhu for the kind invitation and the department staff, the organizers for the kind words and the introducing staff for introducing me to this gathering. And as I've been introduced, I'm Professor Chandramouli, right now working at PES University as a professor of Department of Civil Engineering. Over a period of 15 plus years, I've been into the industry and was responsible for the structural health monitoring job and business, and as well as advanced rehabilitation engineering. Now, although the theme of this FDP is digital transformation trends in construction industry, I wish that we could have all met in person and shared the knowledge offline. Since as you all know, human connections and connecting with human is the highest means of effective and efficient transformation. So, nevertheless, I'm very much pleased to share the knowledge through this online FTP. Now, I'm very happy to be here on this Friday, the first day of the Navaratri. Now, I thank you all for joining and taking time from your busy schedule to attend this online FTP to share more about digital transformation in civil industry. Today, I'm going to walk you through the introduction. Basically, I will be looking into the basics of structural monitoring and the Internet of Things in construction industry. The topic is going to be quite simple and it will be easy for anyone to understand and as well as implement if in case they are really required to implement. Before I start my presentation, and I would like to thank all my teachers. As you all know, I must be acknowledging to all my teachers for their contribution, because today whatever I am because of my teachers. So I would start my presentation with reference to all my teachers. And before we start our presentation, I would like to introduce to a few of my projects that I was involved in, and this would help the participants if in case they require some information or clarification. That is not just limited to this presentation, because this presentation is going to be an introductory to the structural monitoring as well as the IoT. So if in case you need to have specific clarifications on any type of projects or anything related to this particular stream and my specialization, I'd definitely be happy to discuss and clarify. Now, the few of the projects that have been involved in the earlier days are the structural health monitoring of Route 2 Bridge in Vietnam, and the online monitoring for the Golden Horn Bay crossing that is in Russia. Then online monitoring of Nevas Cable Stay Bridge in St. Petersburg, Russia again. And the new Mariinsky Theater in St. Petersburg, Russia. This is one of the largest theaters. And the online structural health monitoring of a Crucial Bridge, which I will try to present today as a case study if in case the time permits. This is the load testing and the periodic monitoring of Route 2 Bridge, that is ROB Bridge in Jammu and Kashmir. The structural health monitoring of a 120-meter span steel truss bridge in Mangalore in Karnataka. Then some of the load testings have been conducted in various bridges, and very few to name is the viaduct that is of BMRCL to evaluate the dynamic augmentation coefficient. Then the vibration monitoring of various industrial buildings for various reasons, and only few that are quite interesting to be presented to the to develop the business as well as quite knowledgeable and where things would fail. So I've taken only few. This is vibration monitoring of an industrial building. And some of the studies which we have supported indirectly or subcontracted on the measurement and the investigation of human comforts to vertical vibrations caused by the electromechanical equipment for various buildings. But this is one of the case studies that is quite interesting. Then we have done a lot of support to the research candidates who would like to do their research on something related to the sensors and the sensor-based vibration damage detection techniques, that is forced and free vibration of latex modified fiber reinforced priestess sleepers that we have conducted at Bangalore University, and we were the supporting team for them. We have done a lot of block tests on the soil properties to understand the dynamic properties of soil. We have done block vibration tests and various studies on the measurement of street pole, because this is quite a good business in various countries. So we have done street pole vibration analysis for various clients. So we have also done on the effect of floor vibration due to moving vehicle because of the construction that is happening. So therefore, if in case I provided just a few glimpses of the previous projects that I was involved in, and I'll be happy to share my experience and knowledge, not just limited to this presentation, which I'm going to present right away. Now, the topic of my today's presentation is structural monitoring and Internet of Things in construction industry, or the civil engineering. Okay, so just to get a confirmation, am I audible and my voice clearly visible and my presentation on the screen?
Sir, it's all okay, sir. Voice, audible, screen, everything is clear, sir.
Thank you. So thank you. So now we'll continue. So the outline of my presentation is going to be a general introduction to structural monitoring, then introduction to IoT. Okay, so introduction to structural monitoring, introduction to IoT technology, general application of IoT technology, case study, and concluding references. I'll be closing some few references that you can refer to. Now, general introduction, most of us would like to know what is structural monitoring is all about, because I believe that not all would be aware of this subject. Although, they would have a basic idea. I will try to do my best to introduce as well as give an understanding to those people who are just new to the subject. Now, as we all know that the civil industry is a evergreen and ever growing. We built what we call as the living champions to all. Now, if you take a closer look at the previous pandemic, now there are a lot of people who couldn't survive, but the only thing that survived is your buildings. And where you were safe and you were in heaven is you are in your home safe. So what we build is the living champions, and therefore civil infrastructure and the construction technology, which has evolved over many centuries, are right now is in the phase faster than what we thought earlier. So it is developing at the rapid phase. So therefore, the civil infrastructure and construction technology have evolved through these centuries and are at a phase faster than ever. Faster than ever in the most of the recent years. Because because of the pandemic, there was a lot of projects that was held back, and during pandemic, the long stretched roads were constructed because we had so much of time and we had less vehicles. So there was a lot of things that happened at the fast rate. The civil infrastructure is expected to hold the largest market, as you all know, in the next coming decade across the globe, because we had a complete close down. There is a lot of infrastructure that needs to be developed for the development of the various nations. So actually, it is projected that India will be one of the world's third largest construction market by 2025. This was projected just before pandemic, and because of the pandemic, this could be extending about 2 or 3 years. But by the way, we are already reaching there. Now, generally what we call the civil infrastructure, it includes all those facilities that I'm talking about, or the critical structures such as bridges, dams, tunnels, highway, and buildings. Now, in the construction industry or the civil engineering, what is the status today is that due to rapid urbanization, there is a necessity for new construction, and for those structures that are already existing, that needs to be retrofitted. So we have new infrastructure and we have the aging infrastructure. Now, as we all know, the present day structures and the recent development in the construction technology has enabled the construction of modern structures. It consists of modern complex design. It includes the complex geometry and conditions, and it incorporates the complex systems such as the control devices and composites. Composites are extensively used in the present day, and the control devices are extensively already started implementing even in India. So, and it is built with advanced materials. We are going as close as 100 MPa, and the performance and durability are always taken care of. So, and we are supported with more sophisticated analysis and design, and also supported with rapid construction methodology. We are able to raise the buildings in a week time. So therefore, it's quite a complex situation, and these structures are subjected to what is called aging, and as well as to accommodate the modern, the volumes and the uncertainties that are there, that are present, and these structures are subjected to various conditions. And by the way, today we are able to reach the targets of greater than 1 kilometer of tall structures and the span of more than 2 to 3 kilometers on bridge. So therefore, but the deteriorating infrastructure that is there, which is already existing infrastructures are deteriorating. So therefore, this deterioration is a worldwide problem, and it particularly in the developed countries as well as in the developing countries. Now, especially in India, because of various contributing factors over which we could have had control over, we have control over, but due to various reasons, and during pandemic also, we had so many structural disasters that happened, that could have been controlled if in case we had a proper maintenance regime. If in case you had the proper maintenance scheme, I think it would have been. We would have averted all those disasters that happened. Very simple example is the Vizag industry. What happened because of the gas leak and how many people leaked, and because there was not proper maintenance. And you can read the report, and I've not included those just to cut short my presentation time, because I had to cover from structural monitoring to IoT and then give you some case studies. Now, the structures are designed to sustain load as per the code and standards, okay, and are subjected to the aging and harsh condition. So now, if you see that initially, whenever you construct a structure, you basically design it to certain capacity. Now, it has an initial capacity, and due to time and due to various factors, it tries to lose its capacity. That means the capacity goes on reducing because of the aging process. And as you all know, it is also subjected to various harsh conditions. Okay. Now, because of that, there is an accelerated deterioration that would take place. As you all know, the load variation pattern is going to be always varying, and it is always continuously increasing. Although it is varying, it is continuously increasing, and therefore that also contributes for the deterioration of the structure. And as you all know, since we are dealing with the variabilities and the uncertainties, the parameters of interest, that is the loads and the capacity, can be best defined by the frequency distribution curve. And as you all know, and that frequency distribution curve is nothing but a probabilistic distribution. And as deterioration progresses over a period of time, if you see the yellow line, as deterioration progresses, now with time, the demand, now you can see the demand exceeds the capacity. So therefore, there is the chances of the failure. So because of that, okay, the demand exceeding the capacity, and it is evident that the time varying probability of failure increases. Now, as we all know, the design must guarantee the performance, that is functionality and strength and durability. Now, structures in general are intended to perform safely during the design period. And you know that we call it as a life cycle, complete life cycle. When it enters its service, basically when you see this slide, I'll try to on the laser. Okay, when it enters the design life, or it starts performing, or when it is designed, it is initially at its, you can say it is at perfect, and it's in good agreement with the engineer's expectation of the day. Okay, and over the period of time, the structure loses part of its initial capacity, Okay. And then when the structure is found to reach a limit of acceptable minimum performance, it undergoes a repair to recover its initial capacity. Now, if it is neglected during this process, I know, no, you may have to see further further progress in the deterioration, and it would lead to various further failures. Now, as you all know, once in a design life, it has to be subject to some type of extreme event like an earthquake or the tornado. Once we have it undergone some type of an accidental loads, and therefore we call for the investigation, and then further, if in case there is a required, we need to retrofit, and after the extreme event, and therefore the same cycle repeats. That means after the retrofitting, the deterioration process continues. Now, what you have to notice here is based on this, a structure that is initially designed deteriorates over a period of time, and once it is inspected, it is also retrofitted, and then in a lifetime it will be subjected to some random event, and therefore after the event, if in case there is a possibility of inspection, there is a possibility of retrofitting, and further it starts deteriorating. Now, what is interesting is, now what is more uncertain or is the time at which the structure starts deteriorating. So we are not aware at what time the deterioration will take place, and at what point we should start looking into the structure or inspecting the structure. Now, as you know, the rate of change of these deterioration is not clear, because the X parameter and the Y parameter, that is what is the capacity and what time it starts, up to what point it will start deteriorating, and the rate at which it is deteriorating is all uncertain. Now, in order to have the exact knowledge and how these things are working, so we need to go for a probabilistic approach, which is dependent on the data and information. Now, the reactive-based maintenance is basically still a reality in civil engineering, and it's still being practiced even in the developing countries and developed countries. But the preventive, that is the time-based and the condition-based, still is not often practiced. But but present day, what is required and the technology what is available can also give us the chances to get into the predictive or the forecasting based method of maintenance. Okay. So we have various questions here: at what time it is going to deteriorate, and when it is going to deteriorate, when to start maintaining, and when to start retrofitting, how much it is retrofitted, and what rate it is deteriorating after retrofitting, and a lot of parameters are involved. And for understanding it better, we need a probabilistic approach. For probabilistic approach, we need lots and lots of data. In summary, in general, civil infrastructures are subject to various conditions, that is aging, increasing demand, aggressive environment, and other factors, which would lead to the damage and deterioration. And if in case we have the inadequate performance assessment, there are various cases I have maybe in the later days someday when I make some presentations, or you can join some presentations. I will definitely give you some of the examples. In various of my presentations I've done that. So I-35 bridge is one of these great examples. So where you have the inadequate performance assessment, and consequently there is a decreasing capacity and increasing the risk of failure, and the final consequence is the failure of a system. Now, as for an engineer's problem, obtaining reliable data is always the first and the fundamental step of finding a solution. So we need basically more information, and from more information we get the more knowledge, and from knowledge we can understand failures and how it is going to behave. Therefore, the failures and their analysis will lead to an insight, and it will improve the design of the structure that we are trying to look into, or the future structure that we are going to design. Now, in most experiments, or in most of the experiences, certain quantities are measured, and then other quantities are determined from the measured data. Now, as we all know, we do the experimentations, or we try to get it from various other sources. Now, associated with each of these the measurements, what we do, we have the measured uncertainties also. Now, when a final result is determined from the measured quantities that has got uncertainties, and that will also result into the results that are uncertain, or lead to an uncertainty even in the desired result. So whatever you're looking for, because of these possibilities of uncertainty getting into the measured parameters, your results are also uncertain. So, or you can say that uncertainty in the derived results. The procedure by which the experiments or the researchers determine the uncertainty is the final result for measured uncertainty, and it's basically called the error analysis or the propagation of uncertainty. As you all know, if in case you are making a measurement in the present, and as we all know, the uncertainty also increases over a period of time, and in the distant future, this uncertainty is going to be quite high. So therefore, because of these uncertainty involved, the result also, the derived result is also having the highest possibility of uncertainty, and the propagation of uncertainty, you can see that it's going to be clear over a period of time. Now, in the present day, the structural health monitoring or structural monitoring of civil infrastructure is being presently accepted by majority in civil engineering faculty as the potential method for assessing the condition of the structure. That is, the monitoring using sensor technology is the way to get the quantitative data about our structure and help us in taking into account the data and then converting that to informations and take informed decisions about the health and the destiny of that particular structure. So basically the objective of this health monitoring is lowering the maintenance cost and increasing the reliability of the structure by using those data. And those data are also having the possibility of uncertainty, because you are also taking the time of the propagation of uncertainty, because you're taking the measurement at that time with the uncertainties and you're taking a measured action. Therefore, there could be it could help in the design of a new structure as well as on the existing structure. Now, the development and implementation of structural monitoring for surveillance, valuation, and assessment of the existing and newly built civil infrastructure has attained to some degree of maturity. That means we are already implemented. There are various countries that have extensively used structural health monitoring. I was also one of the key members in the marketing as well as in developing as a development scientist and as well as the manager for a department for this particular business. So it has been completely implemented in various advanced countries and as well as in a few of the cases in India also, although it is not fully recorded, but you can see that this is presently being implemented, and in research also we have attained to some degrees of maturity in civil engineering. Now, for those people who are very new to this technology, the structural monitoring is just as similar to that of a doctor. Today's engineers are able to continuously monitor the prevailing condition of the structure. Now, because the uncertainties are involved in it, so the continuous monitoring is the present trend. And sometimes, in order to have a periodic monitoring can be done if in case you have certain health issues. And similarly, the bridge can also be monitored at certain intervals. So basically, health monitoring is a predictive prediction of an ability of a system to survive or check the performance requirement of its performance in the future also. Now, let's look into some of the core definitions and the components and the classification and the benefits of structural monitoring. Now, we can define the structural monitoring or structural health monitoring as a technology-driven automated solution where whereby sensing devices are installed and remains in place on or in the structure with the intention of capturing structural data on a continuous basis over a period of time for the purpose of objectively and accurately assessing the structural performance. This is the right definition. This encompasses various things which I've already introduced to. So I hope that this definition would help you to understand what is structural monitoring. Now, structural health monitoring is basically a combination of psionics, that is structural engineering, electronics, and the data science. Now, psionics is a term that was coined in 2003. That is the application of the electronics in civil infrastructure or civil engineering. Now, the monitoring were applied, the health monitoring was applied for the usage monitoring, health monitoring, the quality verification, or the maintenance monitoring, that is reactive, proactive, corrective, preventive, and predictive maintenance. So these are the monitorings were extensively used for various purposes. Now, while most of the engineers will agree on the definition of structure, now, as I said, the monitoring purpose was many. Now, the word health had different connotations and meanings. Actually, it meant differently for different people. So, to counter this problem, many practitioners today, that is, who are into these the core health monitoring, they would try to simply avoid the word health and simply refer to the structural health monitoring as structural monitoring, to avoid the confusion. So this is well documented also, and you can check out, and there is a lot of debates about this, why this decision could be a good one. As I said, the monitoring schemes were utilized for various purposes. Therefore, the health, which is having a it's having a widespread meaning, and as well as it will be quite confusing to specific cases. So therefore, structural monitoring was presently being used for. So therefore, we will call it as structural monitoring. And if I mention as structural monitoring and structural monitoring, it means the one and the same in the initial stage. Now, the application of structural monitoring to civil infrastructure does not rule out the routine inspection or visual inspection, NDTs, the non-destructive evaluation, and short-term monitoring. So most of the time, in various cases, when I was into the projects, so I've seen most of the engineers asking that if in case we are installing some monitoring schemes, they expect the system to perform well and give us a complete report on what is happening on the health of the structure. But that is not so. It also includes all the other routine things that is done for the damage assessment and the retrofitting schemes. Now, the structural monitoring related terminologies that is being used in various domains, as well as in this particular civil engineering domain, is that non-destructive evaluation. And it could be also meaning structural monitoring or measurement, and structural health monitoring, condition monitoring, or damage prognosis. So the same word, the structural monitoring, also can encompass these many streams. That means if in case you are reading any document related to non-destructive evaluation, it also falls into the category of structural monitoring. If in case you're working on condition monitoring or the damage prognosis, that also falls into the category of structural monitoring. Now, each monitoring project presents its own peculiarities, and although it is possible to standardize most of the elements of the structural monitoring system, each application is unique in its own way. Okay, and basically, it is how you can possibly classify the monitoring of a civil infrastructure according to the several categories and subcategories based on the type of monitoring. And that is, you can have a scheduled monitoring, and that is based on the time schedule, the sampling rate, the objects, the phenomena, instruction, and response. So therefore, now you know that, if in case you're going for a particular bridge and you're trying to monitor only the stresses onto it, therefore you will call it as the structural monitoring, or you will call it as bridge monitoring of stresses of a bridge. So therefore, using these classifications, you can combine these classifications, and you can classify or categorize a particular monitoring scheme. So let's say we are continuously monitoring a bridge, we can call it as continuous monitoring of a bridge. Now, if you call if you say that you're monitoring a bridge, or in that particular bridge you are trying to monitor one of these structures, you can say the continuous monitoring of a pier structure subjected to various deformations using the optical sensors and finding its dynamic response. So you can make a combination of it, and by this you can easily make a classification on the structural monitoring scheme, because there are so many possibilities, and not one person could be an expert in various fields. I myself, although I have been into various projects, I'm still limited with my knowledge because of the diversity and the vast amount of things that is involved in this particular scheme, that is structural health monitoring scheme. Now, the modern structural monitoring system consists of 6 main components, and that is the structure. The first is the system, what we call a system or a structure, and the next is the sensor, the data acquisition system, we call it as DAQ, and the data transfer and the storage system, data management system, data analysis and diagnostics, and finally, and you get into the final diagnosis, or you get into the system identification or model, development of model, or the conditions or predicting the remaining life. Now, as you all know, SHM, basically that is structural monitoring or monitoring system, is it's basically a networked, well collaborated, multidisciplinary activity. Now, by this you should understand, if in case you want to develop a monitoring system or a monitoring scheme, or you want to develop a monitoring business, now you should be aware what are the different multidisciplinary activities that will be involved in, and you will understand that how much of complications are involved in it, and how much of well collaborated and well networked system you should have in place just to develop your business or your monitoring technology. And basically it consists of components, and you have the hardware, and then you have the disciplines that should be involved. So you can see that various disciplines that are involved. Since we are dealing with civil infrastructures, we need civil engineers. And since we are dealing only with structures, let's say, and in that we are dealing only with bridges, therefore we need a bridge expert. Now, if in case we are dealing with the monitoring of the environmental conditions, that is the noise pollution or the air pollution, then we need an expert in environmental science, that is civil engineer with the environmental science expertise. So we have this particular infrastructure here. What I meant is that you need to have that expertise in place, and then that expertise will have an opinion on what to sense and what to take the recording from, or what is the quality he needs to look into, what are the threshold values. So you will give the input, and later you need to communicate with the sensor technology guys, and then sensing technology, and further then to communication technology, storage guys, signal processing, and then the few people who are involved in statistical analysis, and as well as the power technology. So these many people are involved, and the disciplines are involved, and the hardwares are nothing but in civil infrastructure. We need the infrastructure. If in case you are trying to look at the water quality, you need some water body, and then for that you need, for sensing, you need to get the sensor, and then for transmitting the sensor data, you need the cables, and to store the data, what is got, we need storage devices. Then the signal processing, if in case you have a lot of noise, that is as you know, in the morning we had the lot of noise in my mic, so we need to have some filters. And then further, when we have done all these things, we need to look into the data more from the statistical point of view, because we're collecting the data over a period of time, and we need to take this data, and all these are supported with the power backup. So therefore there are so many things, there are so many components that are well collaborated, and as you can see, that is, we have various components, hardware, and various disciplines. And basically, whenever you want to develop a business, or you want to develop a scheme, or you want to develop a system, or you want to do a project, so you need to have a well networked, well collaborated, multidisciplinary activity. Now, the first component of a structure. Most of the time, people, when I began my presentation in the earlier days, I already told I've been educating people on structure monitoring over a period of time just to build business, because the business in India was quite low in the earlier days. So we had to educate people, and even today there are few people who are not aware of these technologies, because we have various domains that are having a large market share. So therefore, people get into concrete technology, they are getting the business building sector, they're getting the software industry, they're getting to even big data without understanding this particular system. And basically, as a civil engineer, understanding these common things is very, very important before you get into the mainstream. So therefore, the first question that any engineer will have is that which of the structures are to be monitored. Now, in particularly, there you can practically we can measure or monitor any structure. Okay, so it could be old, it could be new, it could be one particular system, it could be n number of systems connected to each other, or it could be the whole city, or it could be new structure, it could be old structure, it could be a temporary structure or a permanent structure, it could be offline, online, it could be offshore, onshore, and it could be any type of well-connected grid system also. And you can have a massive structure, also tall structure, long structure, or massive structures. Now, the next question that would fall in place is that once you know any structure can be monitored, whether it is micro level or the macro level, whether it is on sun, moon, earth, anywhere, we can monitor these structures. So next is when and what stage these structures need to be measured or monitored is the next question. So as you all know, just as a doctor are able to monitor the prevailing condition of the human at any time, and if in case you are in the happiest moment to the saddest moment, you are in a panic stage, or you are in a distress stage, or you are in the extreme stage also, you go for an examination, and then you would be given with the diagnostics, and then you'll be given some remedial measures. Similarly, when it comes to the monitoring, now as you can see here, we have the phases of life and of the man as well as the structure. You can monitor at any point, that is from birth to death. We can monitor, that is birth monitoring, as you see in the medical science. Here it is process monitoring. Health checkup is nothing but operational monitoring, and then the construction monitoring. And when it comes to some type of illness or some type of issues, the critical issues, we have the clinical monitoring. Here we call you can say that you have the monitoring that is critical monitoring also. So therefore you can see the parallelism between the medical activity and the structural health monitoring business. So now at what stage, if in case you want to ask a question at any stage, now you have a design stage. Now you can do a monitoring. You've been basically designing it and you've been monitoring it. So you can also do the monitoring scheme, and presently people are developing a lot of systems and they've been looking at what happens at every stage, right? So using the software. So modeling testing stage. So people develop small prototype models in order to check how their design is going to be working. So if in case they have a mock-up model, they go with a prototype model, and once they have the prototype model, they would try to do testing on it and get to know how it would behave, and they would validate with their software. So then the construction stage, we are in the beginning stage of construction, so therefore you would like to monitor what is happening. Then the commissioning stage, just before you would start allowing the traffic, so you'll do a commissioning stage monitoring. In service stage, during service life, you'll be monitoring. Maintenance stage, if in case there is a maintenance regime or you have the clauses that is being put in the tender document or in the PWD departments, and the various clauses that is put, you try to monitor during the maintenance stage. And propagation stage. Now propagation stage is for those, if in case you are expecting some type of propagation that is happening, any type of propagation, including the cracks propagation or the corrosion propagation, you can monitor that. And then the retrofitting stage. So if you have a retrofitting stage coming up, you can do a before retrofitting and after retrofitting to understand how best the retrofitting scheme has worked out. And if in case you're mobilizing a structure, these days the trees are being mobilized, the old monuments are being mobilized to a safer place. You also mobilize structures. This day is a present day trend to move the whole building, to raise the building also to certain height because of the change in the road levels. So therefore, that is also called structural mobilization, even from the horizontal as well as vertical mobilization. So you can monitor before and after and during the mobilization also. Demolition. The next is the demolition. You know that there is various projects that is being demolished. It's been on the WhatsApp group that China has demolished various of their projects. So the demolition, when you are doing, you need to monitor what is happening in and around or surrounding the particular building. There might be a lot of vibrations that could transfer to the next healthy building, or there could be a lot of pollution that could happen. There could be noise, and you need to monitor and you need to keep everything in norms. So therefore, you need to understand this demolition. We try to monitor before a demolition takes place and after a demolition takes place to the adjacent structures or to the adjacent surroundings. So basically, we can implement the monitoring to the entire lifespan of a structure from the beginning to the end. So at various stages, we try to plug in some monitoring scheme. We have a new name to it. As I said, you can have the various combinations of what we categorize, and then you can make a combination and you can define your structural monitoring scheme or a project. So therefore, when you see there is a construction, there is a service, and there is a renewable period of a structure. So you try to monitor either the ambient or the traffic or any of the other loads that is going to come onto the structure. And if you want, you can also continuously monitor these things as well as what is happening with the structure. Or else you can also monitor during the initial stage, that is at the construction. So construction monitoring, the commissioning monitoring, inspection monitoring, Damage monitoring, if in case it is in the service, and as well as before the renewal, you can do the damage monitoring, and after the renewal, you can do a retrofitting monitoring. So you can see that. So when you do these, you have something called, during commission, it's called as proof testing, and during inspection, it is called as load testing. During damage, it's called as diagnostic load testing. So therefore, and after the retrofitting scheme also, it is called diagnostic load testing. So therefore, you have the measurement and monitoring construction event, measurement and health monitoring, damage detection, retrofitting, evaluation. So you have a specific reason to do these monitoring, and as well there are particular schemes which is continuously monitoring, that is from the starting day to the ending day. Most of the projects that have been into is on the continuous monitoring, as well as few of those projects on the load testing and diagnostics, just to check what is happening with the damage or why it is getting damaged, and few for the retrofit evaluation techniques. Now, which of the components or the section of the structure can be measured is the next question. Now we have understood what type of structures we can monitor and when to monitor, and now we are looking into what type of structure, which particular section of the structure to be monitored. Either you can go for the whole structure to be monitored, or you can take one particular portion of a structure to be monitored. You call it as global monitoring and local monitoring. If in case you have some specific conditions wherein you want to take a look at what is happening at a particular point, you can go for the local monitoring. If in case you want to know what is really happening in the whole structure in the global level, you can go for global monitoring. Now the next is a sensor. That's a very prime important component of the whole scheme, which is nothing but sensor, and it's a first level device which collects a response of what you want to measure. So therefore, what is a sensor? First is that's the question, and next is the type of sensors that is available. Now, if you look into the general books and the textbooks definition, in general, sensor is device for sensing the physical variable of a physical system or an environment. Then, if you go be very specific, you can refer to the Institute of Electrical and Electronic Engineers, and they give a very formal definitions, that is electronic device that produces electrical, optical, digital data derived from a physical condition or event. Data produced from sensor is then electronically transferred by analog devices into informed output that is useful in decision making done by the intelligent device or individual people. So this is the definition that is given for the present day sensor. The basically, whenever you look at the sensor, if you look at the sensing devices or the sensor, there are various words that you'll come across. The first one is the sensor. The next is the actuators. The technology that is a complement to a sensor is actuator, a device that converts the electrical signal into actions, often by converting signals to non-electrical energy such as motion. So why is it required when you're doing health monitoring scheme, or when you're having, the first thing what you choose is the sensor. Now, when you get into the market, you listen to these words, or when you're talking to some of the electronics experts, they give you a definition. In the initial days, I had these issues. Even today, because I'm not an electronic guy, but I'm a structural engineer. So what happens is that there'll be most of the time there'll be certain things that we won't be knowing. So it is better to understand few things beforehand before you get into this business. The next is these transducers. So people commonly call the sensors as transducers, but there's a particular definitions for it. So sensors and actuators belong to the broader category of transducers. Sensor converts the energy of different form into electrical energy. A transducer is a device that converts one form of energy into the another. So we should note this, and the loudspeakers or the speakers what you have is a form of a transducer. So you can just refer to these definitions in the later days, maybe after you move out of this presentation. You can just Google for it and get these definitions. It will help you. I'm just giving you the flow of understanding this structural monitoring scheme, and then get into IoTs, because there is a difference between the IoT as well as the scheme that we were involved in. So there are various types of sensors that is available present day, and it is exhaustively available, and it is available in the open market. So you have to just talk about the sensor, and you need to give the specific reasons for your sensor type. So like if in case you want to monitor the position, the occupancy, the velocity, force, pressure, flow. So you get a particular type of sensor in the market that you need to buy, and then plug into your system. So there are various type of sensors. As I said, this is a type of sensor, and I've given the examples of that. Now, although we can purchase sensor, but what should be there in your mind is that it should fulfill what is called as A to E characteristics. So it should fulfill A to E, that means A, B, C, D, E, and these are, first is the accuracy. It should be it should be reliable accuracy. And benefits is going to be benefits. That means it has to, the pricing should be quite reasonable, and it should be compact. The shape of it should be enough. Why? Again, if in case you're going with a very small experiments and you have a huge sensor, there is going to be a lot of manipulations into your structural parameter. Therefore, the sensor has to be as light as possible. And then durability, D is durability, that is serviceability of the sensor during the pouring of concrete, as well as during the service of the lifespan of the structure only is almost about 100 years. So you expect that. And then the express, that means you need to have the sensors to, it talks in terms of seconds and milliseconds. Therefore, it has to operate, and the measurement should be in real time. There should not be any lag between the time at which it is recording as well as it is transmitting. So this is the rate at which it is monitoring also should be quite high, and that's what we call it as express. Besides that, it must have adequate service life. With all these things, it would have, the sensor itself has a service life, so that should be adequate and for us to implement in any civil infrastructure. Now, the next thing what you should note is that the sensors cannot measure damage. Okay, so that's very, very important. In most of the cases I've been into, people ask, once we put a sensor, can we see that, look at the damage? So you cannot look at the damage the moment you put the sensor into it. But these sensors sense the changes in the physical variable of a physical system that you are interested in. That, let's say you have a building and you're interested in the strain parameter. So this is the physical variable that you're interested on that particular structure or the environment that could lead to damage. So therefore, let's say you are looking for the strain parameter, and the strain parameter, it is going to be affected by the temperature parameter. So you would measure the strain as well as temperature onto the structure. So therefore, you try to sense, how the strain is changing with respect to temperature, and as well as if the straining is happening, you know there is some change that is happening to the structure. Therefore, you basically collect information in context. That means if you want the information is in context in which the data is taken. So if in case you want strain, you would like to look into the strain data. So therefore, the information is in context with the data it's been taken. So therefore, sensors basically don't measure damage, but whereas sensors measures the change in the physical variable of a physical system or the environment that could lead to the damage. So basically, this is the right point for us to understand what is the damage. Now, damage is defined as a change introduced into the system which adversely affect the optimal functionality of a such system either currently or in the future. So basically, we don't define damage as a structure that is being cracked or some, but we would define any structure to be damaged if it is not functioning in an optimal way. So once it is not functioning in an optimal way, we can call it as damage. Sometimes the system are being overly retrofitted. Excessive pricing is done and they are retrofitted, and the retrofitting is done more than what is required. Therefore, you can still define that as a damaged structure because it's not functioning properly and it is not engineering design. So damage can be actually spatially distributed, as you all know, because we are dealing with civil infrastructures which are made up of concrete or steel or any other construction material. This is the damage is spatially distributed on the overall length scale, and that the damage starts with the material level. So, and as well, so this is a special problem. Then the damage can also be a temporal scale. That means it is time dependent. So basically, as you all know, over a period of time, the damage would propagate. So the damage can happen at any point in space and as well as in time. So any change that is introduced into the system now because of various reasons, whether it is because of time or because of space or because of any other condition that adversely affect the optimum functionality, you call the structure to be damaged. Now, basically damage is not meaningful without a comparison. So therefore, now you know that if in case I want to know whether the system is damaged or not, I need to compare between some stage and to the previous stage. So therefore, I get to know whether the structure is performing as before or not. So therefore, the damage is not meaningful without a comparison between the state, that is between the initial stage and the other stage. That's the second stage. Now, generally we talk about the initial stage and the undamaged stage and the damaged stage. So before and after. So that will be the best point. So now damage assessment basically is by feature extraction, as you all know. Now, basically, whenever you want to see whether the structure is damaged or not, we take the data and we look into the data and we see the features into the data, and then through the signal processing and statistical classification. So therefore, what we see is we convert the sensor data into damage information. So damage assessment is by feature extraction. Therefore, if in case you put a sensor onto a structure, you know that it doesn't measure damage, but you need to do the damage assessment, or you need to look into the features or the status signals or the statisticals statistics of the data, and then convert those data into damage information and get to know what is the state of the damage. So therefore, what are the different type of sensors that is available? So if you go into market, if you talk to this sensor expert, these days there are open markets. Earlier days, we need to just look out for those sensor providers and discuss with them and develop a sensor. But these days it is openly available. You can just define it. The sensor experts will definitely give you what is required for your particular application. Now, basically, the sensors, as you can see, the sensors can be defined based on the location related to the structure. We can call these sensors are non-contact sensors. These are embedded sensors. The surface attached sensors. Okay, there are various names that you can go on giving, and it could be the sensors that are embedded at a particular location for the damage location, or between a composite, embedded in a composite. So we call it as non-contact, contacted, that is surface attached, and damaged or embedded sensors. As well, the conventional type of sensors, that is electrical based or electronic based, are there are various types of sensors, that is surface bounded, glued, welded, clamped, bolted, concrete embedded, composite embedded, and these are the things. And present day, these are commercially available. Okay, so there are various types of sensors that is available by various sensor providers. So you can look into it. Those manufacturers, they have a detailed, and there are various types of sensors. You need to be very, very specific on what type of sensor you are looking for, on what is your particular case. Because I myself, have done in the past. I mean, when I started my first business, or when I started my first project, I had done one particular mistake. I used a wrong sensor at the wrong place. But although I had so much of opportunity to correct the data, but still, I still had that was a point that really made me understand what are the different type of sensors that is available. We need to have a thorough understanding of the projects and what are the materials that we are dealing with. So then you can, because there we were dealing with the steel structures, but because of the time limitations, I was told that we need to monitor the piers, and we know that concrete piers are made with concrete, so we used a boltable one. But to my surprise, when I went there, it was a steel structure. So that was quite a disaster. And later we need to fabricate one particular type of system, which in case it performs well with the sensor that we already had, because each of the sensors is very, very costly. So you have to know what are the different type of sensors that is available in the market, so that you don't do the same mistake what I've done. So conventional sensor techniques have limitations in evaluating long-term behavior. Whatever we are using, this conventional electrical or electronic based sensor have a little bit of issues, and that is the electromagnetic interferences, and they're quite sensitive to electrical noise, and as well as these sensors degrade with age. And present day we have a solution for that also. If in case you're going for long-term monitoring, the fiber optic sensors are identified as the most suitable for health monitoring of structures in such particular cases. So, but even this has issues, and I have dealt with fiber optics also practically. I think there's a lot of developments in the recent days. I hope that it is being addressed by somebody else who is an expert in this field. So the advantages of using a fiber optic sensors, what we found is that it has complete immunity to electromagnetic interferences, lightweight, it's very small in size. I think most of you know this. Nowadays, the telephone lines are also fiber optics. The data networking is also by fiber optics, and you know the speed at which we are dealing with. Very low losses and high temperature and radiation tolerances. And then stability and durability against harsh environment, no local electrical power required at the measurement points, and high resolutions, a large bandwidth of signals, and high sensitivity. That's why you see this online programming so effective, because they are using most of the fiber nets these days, and this is a big market. Now, even in fiber optics, we have various types of sensors that is based on these principles of fiber optics. That is surface bondable, gluable, weldable, clampable, and boltable, and embeddable, and composite embeddable. And you can see this slide gives you some of the present day available commercial fiber optic sensors that is extensively used in projects. So we have used it successfully in few of the projects. They have their own limitations. That is case specific to that project. So definitely this has been extensively used in the present day. So the fiber optics is the present day trend. Now, how many sensors are required? Now you know what are the different type of sensor that is available, and next is how many sensors you need to purchase. Now, in order to understand this, the structural monitoring seek to assist in the non-destructive evaluation, aim to detect the damage location and the extent of damage, calculate the remaining life of the asset, and predict the upcoming accident. So that's the whole agenda of monitoring. What we do is we try to do the non-destructive evaluation just to understand where is the to detect the location first. First is the extent of damage. And then once we know the extent of damage, and we would like to know the remaining life, and as well as the predictive future thing. So the damage state is described by answering the following questions, and the level of information needed to extract the information on the damage can also classify the capability of a SHM scheme. So now, if in case, let's look at this. If you just refer to this particular document by writers and Sona, you would get to know that in 1993, he basically introduced a damage state classification. Okay, so which is that level 1, level 2, level 3, level 4, and level 5. Now, progressively, the damage state described by the damage state can be described by answering these questions, and these are well documented in this particular document. So therefore, now the first question, level 1, is detection of damage, but it means to say, is there an existence of damage? Is there a damage in the system? The next one is level 2, is the location of damage. If there is a damage, where is the location of the damage? So next one, level 3, is if there is a damage at certain point, and what kind of damage is that? Now the level 4 is going to be how severe is the damage, and then the level 5 is going to be what is the damage going to do, or what is the useful life, or what is the remaining life of a structure, what we call it as a diagnosis. So therefore, these 4 levels will give you the answer to the damage state, right? So this is one thing. The next thing, what you see from the monitoring level is that you can see with raising the levels, the sophistication is going to increase. So therefore, if in case you're looking for only for the damage detection, so it is quite a simple job, and and if in case you're looking for the damage, it's quite an involved job. Then as you're looking to increase, and as you are expecting to answer these questions, the level of sophistication is going to increase, and the monitoring system is going to get complicated. The monitoring business is going to get complicated, and therefore a lot of exercise needs to be done. Now, the present day is that, the level 1 is extremely used and extensively used by various projects, just to warn about the failure being detected without, so if in case you want to understand, what is happening with the structure, what is really going on. So then you go for the level 1, wherein you plug in some sensors at a critical location and get to know what is really happening at that point, and whether the structure is getting into some, damage state. So that is one thing, but you can also get into these many things, okay? But there are various there are projects that there are a lot of sensors, but they are non-functional. But there are projects, there are a lot of sensors, but they are functional, but they get enormous data, but they don't know what to do with those data. So the larger the classification or the monitoring scheme, the more the sophistication is the scheme is going to be. As you all know, what we saw in the previous slide, the level 1 system, the scheme is simplest, and it is cost effective, as we saw, and it's quite affordable by most of them. And the level 4, what we are looking at this slide, is most complex and costly class. So now, although we have the capabilities to plug in lots and lots of sensors, but the amount of data that gets into, the amount of data analysis that needs to be done is going to be more complex. Okay, now the next component is the data acquisition system. So the data acquisition system, you know that the sensors are connected to data. So in short, the sensors are networked with the data acquisition system where the data are collected and can be retrieved for analysis. Now we have various type of data acquisition system. We call it as portable systems, the offline monitoring, the fixed data acquisition system, offline or online, handheld, offline, online, and real time. So basically in the market, you get data loggers, data acquisition devices, and data acquisition system. So you need to know about the cost of it. When you're looking at the data logger, it's a low to medium, data acquisition system low to medium, and when in case data acquisition system in high projects are medium to high. So ease of use, its data logger is ease of use is very high. So then, as you know, that this one is low. The flexibility, this is going to be low, medium, this is quite high. The flexibility means the number of sensors that you plug in and the number of channels that you're going to increase. So therefore, the channels are going to be, as you see, data loggers have very few channels, whereas the system has got the very high channels. Now, there are various advantages and disadvantages of using these two systems. It is used for various specific cases. So in case you're going with a temporary installation and you're looking for some type of testing or NDT to be done, so therefore you will go with the portable handheld systems. And if in case you're looking for the long-term monitoring and you're looking for some type of analysis or alert systems to be provided, you need to provide with the online continuous monitoring system that should be permanently installed. The next is data transfer. Now, how the data is going to be transferred, whether it is going to be stored locally or it is going to be transferred remotely, is the next question. So the data that is collected from the sensors can be, you can have various schemes. One is the, you have a centralized data acquisition system, you have the parallel connection, but this type of connections are going to be little tedious. Now, why? Because you have the more number of cables that is going to come. So in one of the projects, I had 20 sensors on a small bridge. There was about only 8 meters, and we were supposed to be doing the monitoring scheme for that, and you can know the number of cables that will run. There are projects where the cable weight was quite high, so you can think of these cables to be one of the prime reasons. The parallel system, this is the issue that we have the more number of cables running from each sensors and to the data system. But the latest development on the development later days was the distribution data system, wherein we had a series system, and I was also one of the involved person in the development of such a system progressively. So over a period of time, I have given my inputs into it, and this has helped a lot. That means all the sensors are connected in series, but it has its own advantages and disadvantages. The advantages and disadvantages of it is the advantages and disadvantages of it is going to be we have the parallel system. If in case there is one sensor that fails, there's no issues. But if in case in this system, even if the wire cuts, the main wire cable cuts, you know, the whole system is going to stop. So therefore, this is the main disadvantage. And these days, we are going with the distributed data system, which has a discrete wireless connection, which are sending the data. So there are various networking schemes that we all know, the wired and as well as wireless networks. We have the LANs and the WANs. Okay, and we have the various schemes like, you know, fully wired system. We have the distributed sensor network, and then you have the fully wireless network system. And these are extensively used in various products. And this is the present day trend in the labs as well as in the office as well as in the field. So although my presentations looks neat, but when you get into the labs, you can see that these are the present day conditions. We have so many wires and, you know, so many systems that are pretty huge, and that needs to move onto the bridge to collect the information. Now, I've been working with the systems that are in a series system, and as I said, this is one of the bridge in Australia that I had the opportunity to work with one of the PhD candidates as well as with one of the consultants who understand the vibration of the bridge because of and as well as the temperature loads. So this is the bridge. You can see here there's one single wire that is moving, and you can see there are multiple sensors that is coming out of the single wire. So this is the single network system. This is quite inspired by the fiber optic sensors. So you can see the fiber optic sensors that could run on the bridge. One single strand can run, and you can have the number of sensors on it, and the limited number of sensors over it on a single strand. Therefore, this is also a series system, and This is extensively used even on the field. So I'm just giving you an explanation on what are the different type of sensors that is available that can be used. So basically you can see here it's a single strand, that is the fiber optics that's moving all over this particular block and trying to monitor the strain. You can see there is this is the extensometer, and basically you have a block here. They are seeing how the temperature is varying this particular block. So these are two sensors, but these are the fiber optics. So you can see that we have the single cable coming, and then you can see that it is in a series system. The sensors are there. So you have one sensor here. You can see there are multiple sensors: 1, 2, 3, 4, and 5 and 6. So this is just basically looking at how the blocks are moving. So in a small block experiment, you can see how many sensors are put, and you can expect the data to be voluminous. Now we have a data issue. So now the next component that we need to know as the data storage is, now in civil infrastructure, we have the large infrastructures and the number of sensors are quite huge. Now we have an issue with the deployment. So that means we have large amount of data. So we have the largest structures with the sensors are quite minute. So we may have to have more number of sensors. Now, whereas when it comes to the analysis of the structure, we need to understand that the changes that happens onto the structure is time varying. So continuous monitoring is expected. So when you have the large number of data, we have the large volume of data, and that is a deployment density issue. And when you have monitoring over a period of time, that is for 24/7 for many years, so almost about 20 years or maybe 1 year also, the amount of data that is going to come is quite large. So therefore, you have two reasons related to issues of sensor deployment. The second one is related to frequency of monitoring. So you have the sensor that is deployed onto the structure. So you have, because of the civil infrastructure being large, you have more number of sensors that is related to deployment issue. And the next one is the frequency of monitoring. So how much of data is stored? So if in case you want to have a basic idea, so any sensor would have a minimum of 3 channels. Let's say you have a sensor of 1 channel, and you have the bit of the maximum bit these days presently we are using in civil engineering. The maximum I'm talking about, we are going with a minimum of 8 bit in your lab or 16 bit. But on practice, these days they're going even with the 32 bit. But let's say we are going with the 24 bit, which I was working in the earlier days. So now if you're going with the 24 bit, you can see that per hour we are getting a 1 megabyte of storage. Okay, so if in case I'm measuring the 1 channel per year, you can see we're getting 1 GB of data. So now you can have an understanding, just 1 channel, and any sensor would have 3 channels, or if in case you have 20 sensors and multiply with those sensors, you can just multiply how much of data that is being stored. So data storage is a big issue these days, and you're into offline teaching and online teaching. So how much of data you've been storing on your, even the webinars that you're conducting, you've been recording it, and how much of data is being stored in your local systems or in the cloud. So the next component is the data management. Although you have all the data and stored and everything, you need to manage it. So what is management? Is like you need to have the data. Most of the time you have a data retention policy. Now you have a policy in your college that these recordings will be lasting only for a month or maybe a year or this semester. So data retention policies are a critical component of data archiving. So once you have a data retention policy enforced, all the information you have in your network, you should also record the retention period. Basically, you may have an agreement with Microsoft or anyone else or any type. Similarly, we have, whenever you're looking for structural monitoring, we have an agreement how much of years. Basically, we record the data for almost for 20 years. We have an agreement for 1 year initially, and then for the 3 years, then for the 5 years, and then progressively for 20 years. But you have to understand that data management is not a simple task. It has got, you need to have online, fast, safe, reliable access. You need to give access to them. It has to be cost-effective archiving, storage and allocation, effective long-term retention. You need to have a very good retention period, data recovery and retrieval. If in case there are some issues, you need to retrieve it. Automatic data replication. If in case you need to replicate it, there should be some type of automatic procedure, data duplication and privacy control. So these are the things that are included in the data management. The last component is the data analysis and diagnostics. As you all know, that's the most important component where we try to do the data analysis of what is happening with the structure. So basically in the data analysis, if you look at the above figure, your data is the first image, which is scattered. So whatever data you're getting from strains and various other parameters or anything, any other data which you are thinking of, whichever stream you belong to, you can think that it's quite scattered. Now, if you want something specific, such as a particular record in a database, it becomes more cumbersome. To simplify this, you need to analyze it. So basically, you collect the data, which is in the raw form, you try to analyze. With analysis, it becomes easy to strike a correlation between the data. So you basically get an analytics. So once you have established what to do, it becomes quite easy for you to make decisions such as what path you want to follow, or in terms of business analytics, and what part would lead to a betterment of performance in terms of your structural engineering. But you cannot expect people in the chain above, or always, whoever is dealing with your structural health monitoring to understand these data that you are providing to them after analytics. So basically, you do take the data, which is quite scattered, and later you do put some analytics and, then do some type of information gathering, and as well as take some intelligent decisions. But as you all know, on the chain line, people are not good enough. So basically, you need to provide a data in such a way that, or the data that is transformed into information in such a way that that could be easily understood. So we have collected the data, we have done some type of analytics, and we have also taken some intelligent decision. But the end user or the users between may not know this particular activity. Therefore, we need to provide it more simple. Therefore, we call what we call as data visualization. So you collected the data is being already processed, but you need to provide your end user or the users who don't understand anything about the data. See, basically, it should be so simple that the large amount of data that is gathered and that is being analyzed, the analytics has been performed. Then you need to put it in such a way that the human mind process the image, visual image and visual graphics, as you all know, better than that of the raw data which we had earlier. So therefore, we expect graphs, the lot of graphs or the gauge way of indication. So you have various gauges that you will indicate what is really happening. So it's always easy for us to understand a pie chart or a bar compared to a raw number. So now you may now, if in case you're wondering how it is done, there are experts and there are platforms that will help you these days. As you all have done your master thesis, as well as, if you're doing so, you use your Excel, wherein you have the data in your Excel, and then you convert that to a pie chart and bar chart. Similarly, if the data are continuously being pumped in to your this one, you can show those data variation. Then this data visualization will aid in complete simple understanding of the what is happening onto the structure in real time. So in short, if in case you have a data interpretation and evaluation, let's take you have the structure that has been put with a lot of sensors like temperature sensor, strain sensor, displacement. Sorry. So speed, inclination, and accelerometer. So once you have got these sensors, and once you have put that, and you have a lot of data coming from these sensors, and what we do is we do the interpretation of it. What you do by this interpretation, you can have programmed interpretation. That is, you can detect the anomalies. You can study what is happening with the sensor, where the sensor is being put. You can do a model validation, threshold check, and damage detection also. This could be all done even using some machines. And then later, you pass it on to it and you convert that information. You basically try to do some data analysis on these things, what has been already interpreted in short by these computers, and then you take some action. So this is a basic example of the monitoring scheme. So the structural monitoring systems can be designed to answer two distinct categories. As you saw in the initial stage, I told you today the present day trend in civil engineering is either we have the new structure or we have the old structure. Both are having uncertainties, and we need to look into those uncertainties and we need to develop our system, our understanding of the system. So the structural monitoring system can be designed in order to answer the two distinct problems categories, that is, as a warning tool for the existing structure as well as a preventive tool in a new structure. So therefore, this is what we call in the sustainable development. This is what is being incorporated. Okay, so as you all know, there are a lot of benefits that we can go on talking about these things, but few of those that will help you to understand what are the main benefits. The development and implementation of the structural monitoring system, although it is capable of fully achieving the objectives or whatever you are looking for, and the benefits is quite a challenging task. Although I say that you can really do the monitoring, but the achieving the objective is also quite a challenging task. And we need to have a well coordinated interdisciplinary research or for adaptation of these innovative technology. Every time there is new innovation, that is a sensor or computation, or that is the instruments or the algorithms, we need to plug into it and then get the benefit out of our system. So therefore this is basically the well coordinated interdisciplinary research. In order to get the complete benefit, we need to have a well collaborated system. But in general, there are various benefits. That is, monitoring reduces uncertainty, as you all know. That is what we are looking for. The monitoring discovers hidden structural results. Monitoring discovers deficiency in the time and increases safety. Monitoring ensures long-term quality. Monitoring allows structural management, and monitoring increases knowledge or the knowledge base. So now we have understood what is structural health monitoring. So if I'm allowed to continue, I'll be able to continue. So kindly let me know if in case I can continue. I will be taking about half an hour more, maybe. Is it fine?
Sir, actually the 11 to 11:30 is the interval session, sir.
Fine.
Break session. Yes,
So can I
complete
need to
5 to 10 minutes, sir?
Okay, fine. Thank you.
Yes.
So I will try to run, because I think there is we just lost about 10 to 15 minutes. I think I lost over there. But anyway, but what we need to understand is that the IoT is a different scheme all over. Okay, so it's not similar to what we understand. Okay, so the inclusion of internet connected devices in construction industry, also known as the IoTs in construction, as benefited the industry by reducing the operational cost, enhance productivity and efficiency, project management. So the Internet of Things has been regarded as the extension of internet and can be significant change to the world, actually. So basically we have a lot of sensors that is being deployed, as you all know. So the IoT platform refers to the system that can connect to physical objects via a network. And basically we had the network system in the structural monitoring, but here what we do is in the IoTs, basically the physical objects are connected, and therefore we receive, manage, store, analyze data generated from the physical objects that has been connected. So therefore what we do is we have been using sensors, okay, networks and analytics. IoT provides a core tool to automate the data collection and generate insight. So basically previously we just were collecting, but we are trying to use some of the technologies that has been that is IoT technologies that can provide unprecedented source of monitoring data in a very detailed level, with a huge amount of data, comes with the ability to interpret in a more meaningful, and basically this provides a business viable purpose. So basically IoT is not just simple like structural monitoring, but as you all know, the market for IoT is quite huge, because the construction industry is the largest in the world, and as you all know, the market for IoT is almost about 8 billion. It was expected to be that, and it has already reached that, and what has been projected in 2025 is almost about 18 billion. Okay, so therefore this is a huge market, and you also already know that you have a major advantage. The construction industry is one of the most or the least digitized, actually. So therefore the need for IoTs is required. So as you all know, the post-pandemic or COVID-19 has precipitated the companies to entirely focus towards Industry 4. That means the focusing the adaptation of digital technology. Okay, so that is what constitutes the Industry 4 revolutions, investing into new products and services that enable them to look for the fast evolving environment that is economical environment. So that means, though, as you all know, basically Industry 4 is a digital transformation, and I will not get into the details of it because of the shortage of time. So I'll just go with the few points, and therefore you will understand. So basically Industry 4 is used interchangeable with the fourth industrial revolution, and we are in that stage, actually. So now what we know is that the industry 4, basically, if you want to know the definition, is nothing but the current trend of automation and data exchange in manufacturing or production or related technologies, which includes the physical or the cyber systems, that is the Internet of Things, cloud computing, and cognitive computing as well, and creating a very smart system. That's the whole idea. We use the robotics, we use the big data and the AIs and augmented reality. So that's the whole idea, and we are in that generation. And with the Internet of Things and the artificial intelligence are the main important factors that is driving this revolution. Okay, so as I said, the IoT is a network that provides resource and information at its very basic level, but it's not just that connected devices, but it provides more of information. So the basic definitions can be looked into, and we have various systems that is connected, and each of the infrastructures are connected, each of the industries are connected. All this can be interconnected. It becomes a networks of network, and the data can be shared among, and it will give you a very clear information. It's a very simple example is that if you have a traffic problem in a certain point, you can easily get the information what is happening at the airport, whether you'll be able to reach, or what are the other routes that you can take. So there are a lot of departments that will be coordinating. All those sensors will be providing the data, useful data that are already that can be easily understood by common man. So I will just skip these things. Or the present day, we have something called Internet of Everything. So it has got 4 pillars, and the people, process, data, and things. But so basically, it is if in case you want to know, the Internet of Things is that it is the equivalent of railroad lines, including the track and connections. Whereas the Internet of Everything is that is related to ticketing and staff, the customers, the weather conditions, everything that is related to if in case you are looking for case you are looking for a travel to the train. Okay, so the essential components are hardware, embedded programming, IoT security, very important these days. That's the present day talk. Networking and cloud integration, data analytics and predictions, artificial intelligence. Okay, so I'll just run through this. These are the sensors that we used: embedded programs, security. I'm sorry, we have a short of time, so I had to. But I will just progressively run through the slides so that you will get to know what I was trying to present. So basically, we have to understand that at the end of the day, from the IoTs, we get the data. Okay, and using we need data needs to be processed. Therefore, we are using the artificial intelligence, machine learning, and deep learning. So artificial intelligence is nothing but the replication of human intelligence in a computer. So the main components of this are going to be the data, the compute, and the algorithms. Basically, what we mean by data is the IoT is going to be a lot of data, and the compute is nothing but the hardware and the software that is being developed. The algorithms are nothing but the machine learning and the deep learning that is there. And you should also note that the data are the asset class. That means you can basically whatever you get from the data, the IoTs that has been the interconnected system. So you know that the present day there are about 6.5 about 7 devices are connected per every person. So that's the present day trend. And in 2025, you can expect 175 zettabyte of data. That means if in case you want to know the equivalent of it, you can have about 25 trillion Blu-ray CDs. Okay. That would be there. That is the amount of data. So as I said, data is an asset and it cannot be wasted, but needs to be analyzed. But you don't want to store because it's a costly affair. And since the data has to be saved or data has to be used, so therefore there is a need for the artificial intelligence and the machine learning and the deep learning to help you out. So in the construction industry, we have been extensively using these, and these are the basics that I wanted to cover, but due to lack of time, I would try to skip it. Maybe some other presentations I would be able to. And this is the present day that we are able to implement the artificial intelligence and get the data from the webcams that are connected, the IoT devices that are connected. So you can get the speed of every, we can also have a counting done, what type of vehicle it is. So this is extensively used, and the same thing can be implemented on understanding what are the different type of cracks, and the maturity of concrete is extensively done by various companies, competitive companies. The concrete, how the concrete is going to be, how the concrete is maturing, you can easily know what is happening. But there is always a question that will the artificial intelligence replace human beings? A very simple answer to that is, when the calculator cannot, that, we've been developing so many systems, but still till date, we are using the calculator. So don't be in that idea that the artificial intelligence is going to replace it, but it's definitely going to simplify the repetitive task. Okay. So I'll just run through and maybe. So the application of IoT is we have smart cities, we have smart, the smart cities, we have various applications, smart environment, we have this, then smart water, then we have smart metering, industrial control, agriculture, and then animal farming. So the home automation is presently the day trend, and everybody knows about it. The e-health after COVID and the security issues. These are main important thing. And if in case you are getting into lots and lots of shopping nowadays, all these things whichever I bought in. So there is a wide possibility of the application of the IoT system, define endless possibilities with this system. We can develop smart cities. That's a present day trend. So I would run through this. This is the case study that I wanted to tell, but I will just skip these things because I would have tried to give from the basics and then get into it. I scheduled it for 2 hours. Anyway, that we have cut for. We lost about half an hour maybe in the initially, and then I think it was, I mistook it as 2 hours. Now I would run through the final conclusion. That will be better. I think I'll run through the final conclusion. Okay, now I would like to conclude this presentation. When it comes to IoT deployment, the rip and replacement approach does not work, but it happens in incremental stage. I wanted to give you some presentations wherein I can say that, if in case you're looking for the previous system that is there already there, just monitoring, if you have to put into IoTs, doesn't mean that you need to just rip it off and replace it with the new ones, but you have to go into incremental phase. There are a lot of issues that are related to IoTs also. In reality, hardware is only one aspect of IoT success. Most of them think that if you have a hardware, you can have a success of the IoT scheme. It is not so. Your sensor must integrate seamlessly with the digital infrastructure that empower the people as well as system to operate more productively. So otherwise, the IoT isn't worth an investment. So the purchasing high quality IoT and sensors and transmitters is only valuable if you can empower people with accurate data that derive business transformation. Ultimately, your digitization, or whatever we are calling as digital transformation efforts has to create long-term values and make life easier for your team. So basically, the mission of any technology is to provide as much as information as possible in the most simplest and most complete form to be used by those to make the decision. So if you take a scenario like this, because of COVID pandemic, everybody would have undergone this. So you've been using a lot of systems. We have a lot of experts, and we have a lot of panics persons. And we can see here, this is one of the conditions where the person is completely in a very bad state, and the family members are in a very distressed situation. And you can see the system, the sensors have been providing data, but we don't know. There is an expert here who could have a minimum expert. So we don't know whether the sensors are functioning properly, the accuracy system are functioning properly, or the interpretation is going wrong, or the expert itself is wrong. So what we need is a reliable information from the reliable source. So you need to have a reliable system under reliable expert. So that's the whole thing. So if in case you want to redefine it, the mission of any technology is to provide as much as reliable information as possible in the most most complete form to be used by those who make the decision. So I think this picture will tell you many things. So now you have the cameras that are in the bags, and the pictures that you got from the Mars. There are a lot of floating pictures in the internet. You can check it out. You can see the resolution of this, and you can see the resolution of this, and you can see why the application and what are the limitations of those. And it also depends. It's quite debatable why we use such systems in bank surveillance and why you use on this Mars. Some people say that you need not have such a system for Mars, but some people say that you shouldn't have this. So it is quite debatable. I leave the floor open for your own mind to give the perspectives. So as I said, the Internet of Things, the artificial intelligence, the BIM, we are at the tip of the iceberg. And the future of IoT, AI, and BIM is not limited. The only limitation is your imagination. So basically, I thank you one and all for your patience hearing, and I'm extremely sorry for the initial hiccup and the time delay for continuing with this. I had to cut short because of the time and the scheduled time. I thank you one and all for your patience hearing, and feel free to contact me for any inputs on any clarifications. Thank you.
So thank you, sir. Thanks for a wonderful presentation. Participants, if you have any queries, you can ask, or otherwise you can post it in the chat box. Participants, any queries are there? So there is no more queries, we can wind up this session. So before that, once again I want to thank Dr. Chandramouli sir for accepting our invitation to deliver your depth of knowledge about the IoT in structural monitoring, and also you have given a high opening session. You have given a lot of the information to the budding engineers who can start their research in this emerging field. Yes, sir. Thank you so much, sir.
Thank you. It's a pleasure to be here. Maybe some other time we will be able to join. Thank you, one and all.
Yeah. Yes, sir. Thank you so much, sir. Thank you, sir. Yes. Participants, so the time is 11:15. I think we have a time of 11:40. We can start in the session by 11:45. So kindly join by 11:45. Thank you. Now you can leave the session.